Hello students, I am Pei Zhang from Tianjin University, IEEE Fellow. I will explain the mathematical interpretation of reinforcement learning in multi-step stochastic economic dispatch. My concern is not reinforcement learning as a fashionable algorithm. My concern is whether a learning-based method can be understood in the same mathematical language used by dispatch engineers: state, action, cost, constraints, value function, and optimality recursion. Economic dispatch with renewable uncertainty is a sequential decision problem. A generator schedule chosen for 1 hour influences the feasible decisions in later hours, and forecast errors in wind power create regulation costs that are not known deterministically in advance. I treat reinforcement learning as a value function approximation method for that sequential optimization problem. The course links stochastic dispatch, dynamic programming, approximate dynamic programming, deep reinforcement learning, and experimental evidence from power system dispatch. The main claim is that deep reinforcement learning can be interpreted as a nonlinear extension of approximate dynamic programming when both are built on the Bellman optimality principle. By mathematical interpretation, I mean three concrete checks: what objective is being optimized, what state information makes the process Markov, and what value function is actually being approximated. Those checks prevent the algorithm from being discussed only by its name. The course has 5 blocks. I first position the problem in the landscape of deterministic optimization, stochastic optimization, and reinforcement learning. Then I formulate day-ahead economic dispatch with renewable uncertainty as a multi-step stochastic optimization model. The third block gives the mathematical bridge: dynamic programming, approximate dynamic programming, Markov decision process modeling, Bellman equations, and the relation between ADP and DRL. The fourth block uses a 9-bus power system case to test whether the interpretation is visible in Q-value surfaces, Q-value trajectories, and operating costs. The conclusion returns to the engineering question: if DRL and ADP share the same Bellman foundation, then DRL is not a detached black box tool. It is a nonlinear value function approximation method for sequential dispatch. The order also matters. If I introduce a neural network before the dispatch objective and Bellman recursion, the model looks arbitrary. If I start from dispatch physics and sequential value, the neural network becomes one possible approximation tool. The classification table separates two issues that are often mixed together: uncertainty and time scale. Deterministic optimization assumes that the input data are known. Linear programming, nonlinear programming, and mixed integer programming can be powerful when load, renewable output, and equipment states are fixed. Stochastic and robust optimization appear when uncertainty must be represented explicitly. Stochastic optimization evaluates expected behavior under random variables, while robust optimization protects against adverse cases. The time scale at the bottom is equally important. Single-step optimization is close to real-time dispatch. It solves one operating interval with current information. Multi-step optimization covers day-ahead and intraday dispatch, where the decision sequence matters. A unit output at hour 1 affects ramping feasibility at hour 2. Reserve procurement for one interval changes the cost-risk balance in later intervals. For renewable-rich power systems, the hard part is not only finding a cheap dispatch at one instant, the hard part is choosing a policy across time under uncertain wind power and load forecasts. That is why the mathematical story naturally moves toward dynamic programming and value functions. This classification also warns against overclaiming. A method that works for a deterministic routing problem is not automatically suitable for stochastic dispatch. The uncertainty model, the time coupling, and the operational feasibility requirements must all match the algorithmic assumptions. The matrix explains where reinforcement learning has real value. For deterministic single-step optimization, reinforcement learning is rarely necessary because the optimal action can often be computed directly by an established solver. In deterministic multi-step problems, learning methods have been used for combinatorial decision sequences, such as routing and graph-based optimization, where the action space is large. In probabilistic single-step problems, bandit methods handle uncertainty in immediate rewards, but they do not capture long intertemporal coupling. Multi-step probabilistic optimization is the natural territory for reinforcement learning. Deep Q networks, proximal policy optimization, actor-critic methods, soft actor-critic, and distributionally robust variance. Economic dispatch with renewable uncertainty falls in this lower right region. The decision is continuous, the cost is uncertain, and the future matters through ramping and regulation requirements. I use this matrix to justify the modeling choice. I am not replacing optimization with learning for its own sake. I am using learning because the dispatch problem has the sequential and stochastic structure that learning algorithms are designed to approximate. The table also separates value learning from constraint satisfaction. Many reinforcement learning algorithms learn a reward maximizing policy, but dispatch additionally requires feasible schedules. In this course, the mathematical interpretation focuses on value function consistency rather than claiming that learning alone solves every security constraint. The dispatch model converts the engineering problem into mathematics. The objective minimizes total cost across the scheduling horizon. Inside the summation, each thermal unit has a quadratic cost curve. The squared output term captures increasing marginal fuel cost. The linear term captures proportional fuel cost, and the constant term captures fixed operating cost. The expectation term is the cost of regulation caused by wind uncertainty. If actual wind power is lower than forecast, upward regulation must make up the shortage. If actual wind power is higher than expected, downward regulation or curtailment may be needed. The random variable xi represents the wind forecast error, so the regulation cost is not a single deterministic number, it is an expected cost over uncertainty. The constraints carry the physical meaning. Scheduled thermal generation plus forecast wind must meet forecast load. Actual wind equals forecast wind plus the error. The positive and negative regulation variables measure how much imbalance remains after actual wind is realized. Thermal outputs must stay within minimum and maximum limits. Wind output must stay within available capacity, and ramp up and ramp down inequalities restrict how quickly thermal units can change between adjacent hours. The model is multi-step because the variable at time t is linked to time t-1. That intertemporal link is exactly what later becomes state information in the Markov decision process. A useful way to read this model is to separate planned decisions from random realization. Thermal generation is scheduled before the forecast error is known. Regulation cost is paid after the error appears. The expectation connects those two timescales inside one objective. Dynamic programming is the classical way to solve a multi-stage decision problem. The diagram is a chain of states and actions. At each stage t, the system state summarizes the information needed for the next decision. The action changes the state and produces an immediate reward or cost. The Bellman idea is that a good decision is not judged only by the current cost. It is judged by current cost plus the best achievable future cost to go. In economic dispatch, a cheap generation setting in the current hour may be expensive later if it leaves a unit unable to ramp for the next load rise. Dynamic programming handles that by decomposing the whole horizon into coupled single-stage subproblems. The optimal solution can be obtained by starting from the final stage and working backward. Mathematically, this is elegant because it gives a recursive optimality condition. Operationally, it is demanding because the number of states grows rapidly with system size, generator outputs, renewable uncertainty, and time resolution. This computational burden motivates approximation. For dispatch, the cost to go is not an abstract mathematical object, it is the future fuel cost, regulation cost, and feasibility pressure created by the current schedule. Bellman recursion is therefore a disciplined way to price the future consequence of a present generation decision. Approximate dynamic programming starts from a practical limitation of exact DPA. A realistic dispatch system cannot enumerate every possible combination of load, wind, previous generator outputs, and future forecast errors. ADP keeps the Bellman logic but replaces exhaustive enumeration with value function approximation. Instead of storing the exact value of every state action pair, it estimates the value by sampled data, simulation, or a parameterized function. That is why it is described here as model-free in the learning sense. It can estimate value from observed transitions without requiring a complete closed-form transition model. ADP is closely related to reinforcement learning because both rely on temporal difference updates. The estimate is improved by comparing the current value prediction with a target made from immediate reward, plus the value of the next state. The trade-off is clear. We give up exact global optimality, but we gain computational feasibility for large-scale dispatch. For power system operation, a near-optimal policy that can be computed reliably may be more useful than an exact policy that cannot be computed in time. The approximation can be hand-designed, learned, or a combination of both. The important point is that the approximator is judged by Bellman consistency. A good approximation predicts values that remain coherent when the process moves from one hour to the next. The reinforcement learning loop is the same sequential structure expressed in agent environment language. The agent observes a state, chooses an action, receives a reward, and observes a new state. In dispatch, the agent is the dispatch policy. The environment is the power system together with load evolution, renewable forecast error, and operating constraints. The action is a vector of generation set points. The reward can be negative operating cost, including generation cost and expected regulation cost. The next state includes the updated time, the next forecast information, and the generator outputs inherited from the previous decision. The Markov property is critical. It says the current state must contain enough information to predict the distribution of the next state after an action. In dispatch, previous unit outputs must be part of the state because ramping feasibility depends on them. This mapping makes reinforcement learning more than a trial and error controller. It becomes a way to estimate a dispatch policy for a Markov decision process. This loop also explains why simulation data are valuable. Historical or simulated transitions give examples of how a dispatch action changes the next operating state. Each transition supplies a small piece of evidence about long-term cost. The Markov decision process formulation is the formal bridge from dispatch optimization to reinforcement learning. The state at time t contains the time index, the load at that interval, the predicted wind power, and the previous output of the thermal units. The time index is not decorative. Load and wind patterns are time-dependent across a day. The previous thermal output is essential because ramp limits make the next feasible action depend on where the unit started. The action space contains the planned thermal power outputs at time t. In this simplified formulation, the control decision is the thermal dispatch that compensates for load and wind uncertainty. The reward is written as the negative of operating cost. That sign conversion lets a reinforcement learning algorithm maximize expected return while the engineering problem still minimizes cost. Generation cost appears directly. Expected regulation cost appears because the wind forecast error creates a future balancing need. When I say reinforcement learning solves this MDP, I mean it learns a mapping from these states to generation actions so that the accumulated negative cost is as high as possible, which is equivalent to making total operating cost as low as possible. If previous unit output were omitted, two physically different situations could look identical to the agent. The same load and wind forecast may be easy after a high previous output, but infeasible after a low previous output. That is why the state definition matters. The Bellman equations are the mathematical center of the course. The Q value evaluates the long-term return of taking action in state S and then following a policy. In dispatch language, it measures the long-term cost consequence of a generation schedule chosen at one operating state. The definition sums discounted future rewards. The discount factor gamma gives more weight to near-term costs while still preserving future effects. The Bellman expectation equation evaluates a fixed policy. It says the current Q value equals the immediate reward plus the discounted expected Q value of the next state under that same policy. The Bellman optimality equation replaces the next policy action with the best possible next action. That turns policy evaluation into optimal control. For cost minimization, the sign convention may use negative cost as reward, so maximizing return corresponds to lowering cost. The neural network, drawn on the right, represents the deep learning implementation. It takes the state-action pair as input and outputs an estimated Q value. The network is not creating a new principle. It is approximating the same Bellman value function that dynamic programming defines. The diagram of the neural network should be read as a function approximator for the Q equation. It does not remove the Bellman equation. It supplies a flexible numerical form for estimating a value that exact dynamic programming would store in a table. The first theorem states the shared mathematical foundation. ADP and DRL are different in representation, not in the core optimality principle. ADP usually estimates the Q value by a linear combination of hand-designed basis functions. The basis functions encode selected features of the state and action. DRL estimates the same kind of Q value using a deep neural network. The table compares those choices. ADP is linear in its parameters when the basis is fixed. DRL is nonlinear because the neural network contains hidden layers and nonlinear transformations. But both methods use Bellman optimality, both can use temporal difference learning, and both try to reduce the mismatch between the current value estimate and the Bellman target. This matters for interpretability. If a deep model is understood as a value function approximator under the Bellman equation, then its role in dispatch is clearer. It is not merely fitting a black box mapping from load to generator output. It is learning a representation of long-term dispatch value. This theorem is the first step toward trust. It says that the deep model and the approximate dynamic programming model can be evaluated with the same value function language. Their outputs can therefore be compared as Q-value estimates, not merely as unrelated algorithmic results. The comparison becomes precise through the value function formulas. In ADP, the estimated Q-value is alpha transpose phi of S and A. The vector phi contains features constructed from the state and action, and alpha contains the weights. If the selected features include load, wind forecast, generator output, squared generator output, and cross terms, the linear model can represent a quadratic cost surface. In DRL, the estimated Q-value is f theta of S and A. Theta denotes all neural network parameters, weight matrices, and bias vectors across the layers. The network learns its own nonlinear representation rather than relying only on a fixed feature vector. The bottom expression gives the common training logic. The Bellman residual is the difference between the current Q estimate and the target made from immediate reward plus discounted next state Q estimate. Minimizing the expected squared residual is the mathematical training objective behind both approaches. This is the reason the two methods can be compared directly. Their function classes differ, but the target they are trying to satisfy is the same Bellman consistency condition. The residual objective is also the place where data enter the mathematics. Each sampled transition contributes a target. Training reduces the error between the predicted value before the transition and the reward plus future value estimate after the transition. The second theorem gives the deeper interpretability result. The function class represented by DRL strictly contains the linear value function class used by ADP. In set notation, the ADP function class is a subset of the DRL function class. The proof is constructive. Start with any ADP value estimate written as alpha transpose phi of S and A. Then construct a two-layer fully connected neural network that reproduces this linear estimate exactly. The input is the concatenated state action vector. That input contains all quantities needed to compute the feature vector. If the network can produce phi of S and A in the hidden layer and then apply alpha in the output layer, the network output becomes identical to the ADP value estimate. The point is not that DRL always learns the same model. The point is that DRL has enough representational capacity to include the ADP model as a special case, and can also represent nonlinear extensions beyond it. The word strictly is important. If the neural network only reproduced the linear model, it would not add modeling power. The theorem says it can reproduce the linear model and can also represent more complex nonlinear value shapes when the data support them. The constructive proof becomes explicit on this page. The hidden layer uses an identity activation, so the activation output equals its input with a suitable first layer weight matrix and zero bias. The hidden layer can be set to equal the ADP feature vector phi of S and A. The output layer then uses a second layer weight vector equal to alpha and a zero bias. Under those parameter choices, the neural network output is alpha transpose phi of S and A, exactly the ADP value function. Therefore, every linear ADP value estimate can be represented by some DRL network parameter set. The conclusion is the subset relation. This is a useful mathematical interpretation because it turns the phrase deep reinforcement learning into something more concrete. It is a larger function class for Bellman value approximation. In economic dispatch, that larger function class may capture nonlinear effects created by uncertainty, operating limits, and interactions between generator outputs, while still preserving the same dynamic programming foundation. This proof is intentionally simple because interpretability benefits from constructive arguments. It does not require mysterious neural network behavior. It shows one explicit parameter configuration under which the network collapses to the familiar ADP approximation. The validation uses a compact power system case so that the value function comparison can be seen clearly. The IEEE 9-bus test system has 2 thermal units and 9 transmission lines. A wind farm is connected at node 3 with an installed capacity of 180 megawatts. The scheduling horizon is 24 hours with 1-hour resolution. The load forecast curve rises from a lower level in the early hours to a peak later in the day, and then declines. That shape creates ramping pressure on thermal units. The wind forecast curve fluctuates much more irregularly, with changes that do not necessarily align with load demand. This mismatch is the source of regulation cost. The test system is small enough for ADP and DRL results to be compared without hiding the math inside a large network case. It is still meaningful because it contains the essential dispatch conflict. Thermal generation is controllable but costly and ramp limited. Wind power is low marginal cost but uncertain. The two forecast curves also create a useful stress test. When load is rising and wind is falling, thermal units must increase output and may hit ramp limits. When wind rises during lower load periods, regulation or curtailment becomes more relevant. The DRL framework is implemented with DDPG, which is suitable for continuous control. Dispatch actions are continuous generator outputs, not a small set of discrete commands, so an actor critic method is appropriate. The actor network maps the current state to a generation action. The critic network evaluates the Q value of a state action pair. Both networks use three layers with two hidden sizes, 256 and 128. The actor learning rate is smaller than the critic learning rate, reflecting the usual practice that the policy should move cautiously while value estimates are being learned. The discount factor is 0.95, giving substantial weight to later hours in the dispatch horizon. The replay buffer stores past transitions so that training samples are not limited to the most recent operating trajectory. Initial exploration noise encourages the actor to test nearby actions, and noise decay gradually reduces exploration as the policy becomes more reliable. Offline training over 20,000 episodes provides the policy before online dispatch decisions are made. These settings affect the stability of the learned policy. A large replay buffer improves sample diversity. A high discount factor keeps future dispatch cost visible. Gradual reduction of exploration noise helps the final policy become less volatile. The ADP baseline uses a linear value approximation, but the feature vector is carefully designed. It contains a constant term, time, load, predicted wind power, previous outputs of two thermal units, current outputs, squared current outputs, and the product of the two current outputs. Those squared and cross terms are important because economic dispatch cost is not purely linear. Thermal production cost is often quadratic, and interaction between units can appear through balancing and constraints. At each time period, a deterministic subproblem is solved by C-plex. The value function parameters are updated through TD learning, using the Bellman residual as the learning signal. Unlike the DRL model, this ADP procedure performs online iterative optimization and does not require offline training episodes. The convergence criteria include cost convergence, Bellman residual convergence, and parameter convergence. The reported result, convergence in 60 iterations and 17.8 seconds, indicates that the linear ADP approximation is computationally efficient for this case. It also gives a clear benchmark for judging the learned deep value function. The feature vector is not arbitrary. It mirrors the cost structure and system memory. Previous outputs represent ramp history. Squared terms represent quadratic generation cost, and the cross term lets the approximation capture interaction between the two thermal units. The three-dimensional Q-value surfaces are visual evidence for the mathematical interpretation. Both surfaces are plotted under the same system state, with the two thermal unit outputs as the horizontal axis and Q-value as the vertical axis. The DDPG surface and the ADP surface are not identical point by point, but their shapes are highly consistent. Both exhibit a clear curved, almost quadratic value landscape. That is what we expect from economic dispatch because fuel cost is quadratic and regulation cost changes smoothly with imbalance. The marked decision points lie on low-cost regions of the surfaces, showing where the methods choose their dispatch actions. If DRL were learning an arbitrary black box rule unrelated to dispatch optimization, the Q surface could have a very different shape. Instead, it resembles the ADP value surface. This supports the idea that the deep critic is approximating the same underlying Bellman value structure while using a more flexible nonlinear function class. The vertical scale is value, not physical power. Moving across the surface means trying different thermal output combinations under the same state. The surface shape tells us how strongly the long-term cost changes when the dispatch point moves. The Q-value comparison over time gives a second kind of evidence. The line chart shows that the D, D, P, G, and ADP values rise and fall in similar patterns across the 24-hour horizon. The exact values differ in some intervals, but the temporal evolution is aligned. That means both methods identify similar hours as expensive or valuable from the viewpoint of long-term dispatch. The scatter plot checks the relation across decision points. Most points lie near the diagonal, and the Pearson correlation coefficient is greater than 0.97. A high correlation does not prove that every dispatch action is identical, but it shows that the two approximators assign value in a strongly consistent way. This is important because interpretability should not rely on a single surface at one state. It should persist over time and across operating conditions. The evidence here says that the deep value estimate and the ADP value estimate are measuring nearly the same dispatch value landscape. Temporal agreement is especially relevant in a 24-hour dispatch horizon. If two methods disagree only at isolated points, the policy impact may be limited. If they share the same daily value pattern, their operational interpretation is much closer. The cost table translates value function consistency into engineering performance. The DRL total cost is 116,349.53 Chinese yuan. The ADP total cost is 113,882.10 Chinese yuan. The difference is less than 2.2%. The generation cost differs by about 2,542 Chinese yuan, while the regulation cost differs by only about 75 Chinese yuan in the opposite direction. This tells us that the two methods allocate the cost components in very similar proportions. They are not simply obtaining similar totals by completely different operating strategies. They are reacting to wind uncertainty in a comparable way. For dispatch engineers, that is the practical value of the mathematical interpretation. If the learned DRL policy produces costs and value structures close to an ADP benchmark, confidence in the learned policy increases. The model remains approximate, but its behavior is explainable through established sequential optimization logic. The small regulation cost difference is particularly informative. Wind uncertainty is where the stochastic part of the model appears. Similar regulation cost suggests that both methods are making comparable decisions about how much balancing burden the thermal schedule leaves to the system. The conclusion has three mathematical pillars and one engineering implication. First, DRL and ADP rely on the same Bellman optimality principle. They evaluate actions by combining immediate reward with future value. Second, DRL can be interpreted as a nonlinear extension of ADP because a neural network can represent the linear ADP value function as a special case and can represent richer nonlinear functions beyond it. Third, the experiment confirms that the two methods generate consistent Q-value surfaces, consistent Q-value trajectories, and comparable dispatch costs. The engineering implication is confidence. A learning-based dispatch method should not be trusted only because it performs well on average. It should also be interpretable in terms of cost, value, uncertainty, and sequential constraints. This interpretation helps place reinforcement learning inside the mathematical framework that power system operators already use for multi-step stochastic economic dispatch. This conclusion does not say that every deep reinforcement learning controller is automatically reliable. It says that for this class of dispatch problem, reliability can be studied by comparing Bellman value functions, dispatch costs, and operating behavior against an interpretable benchmark. The appendix anchors the earlier research status comparison. The references include neural combinatorial optimization, attention-based routing, graph neural network reinforcement learning, distributionally robust reinforcement learning, Q-learning, soft actor critic, and classical bandit theory. They show that reinforcement learning has been studied across deterministic multi-step problems, probabilistic single-step problems, and probabilistic multi-step problems. For this course, the most relevant connection is not any single citation. The relevant pattern is that learning methods become most useful when the action sequence, uncertainty, and long-term value interact. Power system economic dispatch has exactly that structure. The appendix therefore supports the positioning of the dispatch problem in the lower right part of the optimization matrix, multi-step, probabilistic, and value function-based. The references also indicate where extensions may come from: robust learning for uncertainty sets, graph-based learning for network structure, and actor-critic methods for continuous actions. Those directions become meaningful only after the dispatch formulation is clear. I will close with the central message. Multi-step stochastic economic dispatch is a sequential optimization problem under uncertainty. Dynamic programming defines the Bellman foundation, ADP approximates the value function with design features, and DRL extends that approximation with a deeper nonlinear function class. When the learned Q-value surfaces, Q-value trajectories, and operating costs agree with the ADP benchmark, reinforcement learning becomes more interpretable for dispatch applications. It is still a method that must be validated carefully, but it can be explained in the language of optimization rather than treated as a black box. Thank you. For practical use, I would treat this interpretation as a diagnostic tool. Before deploying a learn dispatch policy, I would check whether its value surface, cost decomposition, and the response to uncertainty are consistent with established optimization insight.